Hello dear learners, I welcome you all for this online video session. Today we will discuss about a very interesting topic, principle and theory of Raman spectroscopy. So these are the learning outcomes. After attending this video session, you will be able to understand basic principle, excitation process and origin of Raman spectrum, as well as you will be able to explain the difference between Raman and IR spectroscopy. Now we will see in detail. First, what is the basic introduction of Raman spectroscopy? So as we know from where this name came, the Raman spectroscopy. So it was discovered by the C.V. Raman in 1928. So what is Raman spectroscopy? It is a spectroscopic technique used to observe vibration, rotational and other lower frequency modes in a system. So here we can observe the vibrational mode, rotational mode, or you can say vibrational plus rotational mode. Now, water being a quite useful solvent. Over here, we can use water as a solvent. It's more advantageous than IR spectroscopy because in IR we can't use water. So here we can use water is more advantageous. Signals are usually within far to near IR region. Means whatever signal we will get, it will only in the IR region. Normal modes of the vibration can measure in the middle IR region for organic molecules. So there is no difference in the frequency. So this is the basic introduction about Raman spectroscopy. Now we'll move towards, before principle, we should know the conditions for Raman spectroscopy. Means which kind of molecules you can say Raman active or Raman inactive. As like IR, the molecule which can change the dipole moment are IR active. Like that, what is the condition for Raman spectroscopy is polarizability. Means to give Raman spectra, the molecule should change polarizability. Otherwise, it will not give a Raman spectra, or you can say Raman signal. So for IR, the molecule should change the dipole moment. But for Raman, the molecule should change polarizability. See, here there is a second difference. First difference, we have already seen in introduction part. Water is used as a solvent. In IR, we can't use water. Here, the second difference, the conditions of Raman. Now, the Raman spectra occurs as a result of the oscillation of dipole moment induced in a molecule by the oscillating electric field of an incident wave. Means what? The induced dipole moment is directly proportional to the polarizability of the molecule. Means to produce Raman signal, the molecule must possess anisotropic polarizability. What is this? What is polarizability? Is a relative tendency of a system of a, you can say, electric charges to become polarized in presence of field. And what is anisotropic? So anisotropic means what? It is the extent to which the emission polarization is retained. Means in presence of an electric field, the electron cloud of an atom or molecule is polarized. So which should change during molecular rotation, or you can say molecular vibration to give Raman spectra. So the basic condition for Raman spectroscopy is polarizability. Now we will see which molecules are Raman active. Now I have a question. Which molecules are Raman active? So here is the answer. IR active vibrations are not Raman active. Means what? The molecules which cannot measure by IR spectroscopy will be measured by Raman spectroscopy, and the molecules which cannot be measured by Raman spectroscopy will be measured by IR spectroscopy. So Raman active vibrations are not IR active. Means if you understand which molecules are IR inactive, you can understand the same molecule will be Raman active. For example, the homodiatomic molecule, you can say there is one example of dinitrogen. Means symmetric stretch cause no change in dipole. Means there is no change in a dipole moment. That's why this N2 is IR inactive. But it causes a change in the polarizability of bond. That's why it is Raman active. Means what? It is IR inactive, but as the bonds get longer, it is more easily deformed, and it is Raman active. Now we will see what is Raman effect. As you know, when a beam of monochromatic light was allowed to pass through the substance, see, in Raman also like IR, it will be measured in any state. Compound will be measured in any state, solid, liquid or gaseous state. So when a beam of monochromatic light was allowed to pass through the substance in any of the state, the scattered light contains some additional frequencies. You can say over and above the incident frequency. Means whatever scattering light we will get, in that we will get some additional frequencies, and that particular frequencies, you can say it because of the effect, and that effect is known as Raman effect. Now we will see the principle. What is the basic principle of Raman spectroscopy? So here you can say this is the sample, this is the incident light, and this is the scattered light. Means the basic principle in Raman spectroscopy is scattering. So when a substance is irradiated with a monochromatic light, the scattered light is observed in a direction at right angle to the incident light. And when we are going to measure, or you can say investigate, the scattered light, it was found that the frequency of a scattered light was same as the frequency of incident radiation. Means both the frequency will be same. The scattered light, the frequency of scattered light is equal to the frequency of incident radiation, and this is known as Rayleigh scattering. When both the frequency are same, it's known as Rayleigh scattering. Now we will see what are the other type of radiations. Here we will get. You can say sometimes what happen, the lines of a higher frequency are also obtained. As I said, here there is a line. Means the frequency of a scattered line is equal to the frequency of incident radiation, and that is Rayleigh scattering. But here what happened? The lines of a higher frequency are obtained, that of the incident beam will be scattered, and this kind of scattering is known as Raman scattering. So the lines with lower frequency are called Stokes line, And the line with higher frequency are called anti-Stokes lines. And the lines with the same frequency, as you know, it is known as relay line, or you can say relay scattering. So here this is known as relay scattering, and this both are known as Raman scattering. So Raman lines are divided into two lines, Stokes lines and anti-Stokes lines. So when the line of a scattering light having lower frequency than incident radiation, it is known as Stokes lines. And when the scattering line, or you can say the frequency of scattered light, is higher than incident light, it is known as anti-Stokes lines. Now we will see the very important process, excitation of Raman spectra. Means, or you can say the origin of Raman spectra, how we will get the Raman spectra. So here what happened? You can see by this diagram. Here there are two diagrams, one is A, other one is B. Now what is this A, we will understand. So this is the excitation of the molecule to a virtual level, it's J. This is the virtual level J, and re-emission of photon at lower and higher frequency. Now we will see what is it in detail. So what happened? When any sample, or you can say molecule, is irradiated by monochromatic beam of the energy, and that energy you can say it's HVEX. This is the energy of excitation energy. You can say excitation can be considered to involve this virtual state. Means what happened? When we will get the Stokes line and when we will get the anti-Stokes line, that we have to understand. So when we will get the Stokes line is my first question. So when we are irradiating our sample with this much energy, what happened? You can see over here, this V is equal to 0, means a ground state, or you can say vibrational state, a ground vibrational state. But V1 is the excited vibrational state, or you can say first excited vibrational state. So here from the ground state, our molecule will excite and it will come over here to the virtual state. It's denoted by this J, and after that it will re-emit the photon. Now this is the re-emission of photon, and it will come over here to the first excited state, and this is the energy difference. Means what? Here when the photon lose the energy, when it will re-emitted, it will generate this much energy. This EX means excited energy, or you can say frequency of excited radiation, and this V means frequency of scattered radiation. So in Stokes line what happened? Here the scattered radiation is of a lower frequency than excited radiation. That's why it produced Stokes line. And what happened in anti-Stokes line? So in anti-Stokes line, the molecule, we are applying the same energy, you can say HVEX, this is excitation energy. So first, some molecules are present over here in the vibrational excited state. So when we apply energy, what happened? Molecule will excite from the first vibrational excited state, and it will come to this virtual state. When this re-emit the photons, it will come over here to the ground state, and this is the energy difference. But here the energy will increases, and here the energy will decreases. Means what? Whatever scattered radiation is there have a higher frequency than excited radiation. At that time it will shows the anti-Stokes lines. So you can see over here, this is the energy difference, and here this is the energy difference. Here the scattered light have a lower frequency than excited light, and here the scattered light have a higher frequency than excited light, or you can say radiation. So this is the generation of Stokes line, and this is anti-Stokes line. Now see over here, it's a same frequency, means this is your relay lines. Lower frequency means Stokes line. Same frequency, this is a relay line, and you can say higher frequency means anti-Stokes lines. Now it is clear that lower frequency emissions called Stokes and higher frequency called anti-Stokes. Now we will see one example of a Raman spectra. So I have taken the example of Raman spectra of CCl4. You can say carbon tetrachloride. This is the Raman spectra of a carbon tetrachloride. First, see how it will express. So on x-axis there will be a delta V bar, means there is a difference in a wave numbers, but the unit is centimeter inverse. Now what is the difference? This is the difference between the observed radiation and the source. So this is the wave number difference, delta V bar, in a centimeter inverse, and on y-axis there is a intensity. Now you can see over here, whatever lines we are getting, see, always in a Raman spectra there are three type of lines: Stokes lines, relay scattering, as well as anti-Stokes lines. So always there will be, in middle you will get the relay scattering. On the left side you will get the Stokes line, and on the right side you will get the anti-Stokes line. You can see over here, this side will be in a minus range. Means what? And this is in a plus range. The Stokes line are found at a wave number of this 459, 314 and 218 centimeter inverse. So, but this is in a minus. Means what? This R occur as, means what? You can say these lines are smaller than relay scattering. You can say relay line as well as anti-Stokes lines. Don't see the intensity. Intensity is higher, but energy is lower. The line is having a lower frequency. When we are analyzing Raman spectra, we are measuring the Stokes line only, because these lines have a very less intensity. But see, on the left and right side, both the side, you will get the same lines at the same frequency, at the same wave number, and this is known as the Raman shift. Means the Raman shift are same at both the side, but this Stokes line have a higher intensity. So we will going to measure Stokes line when we are analyzing the Raman spectra. Now we will move towards the mechanisms of Raman and relay scattering. You can see in the diagram, I am just showing the difference. You can see here how the Raman is different from IR. So what is IR? From ground state, a radiation, it will excite. You can say a molecule will vibrate and come from the ground state to the excited state. That will be only first excited state. This is the basic difference between IR and Raman spectroscopy. Here what happened? This is the excitation energy. This is a relay scattering. You can see this is a relay scattering. So here what happened? This is the relay scattering. You can see from ground state to the virtual energy state it will come, and again it will re-emit the radiation, and it's come to the ground state. Now in stock scattering, what happened? As we have already seen, in stock scattering, from the ground state, the molecule will excite and it will come to the first virtual energy state, and it will re-emit and come to the first vibrational excited state, and it will produce at a high intensity lines. Now see, in anti-stock Raman scattering, what happened? It will vibrate, or you can say it will excite from the first vibrational excited state to the first virtual energy state, and it will come back over here at the ground state. So this is the basic difference between IR and Raman, or you can say the stocks as well as anti-stocks line. Here we can understand by the energy difference. You can see over here, for relay scattering there is a same frequency, and for stock scattering the energy difference is like this. Means frequency of scattered radiation is lower than frequency of excited radiation. It's a stock scattering. And over here, frequency of scattered radiation is higher than frequency of excited radiation. So it's anti-stock scattering. So this is the basic difference between the relay scattering, anti-stock scattering and stock scattering. Now you should have a doubt that how this virtual state will come. It's not defined, but depending on the frequency of radiation from the source, the energy of molecule can assume any of the infinite number of the virtual states. It's not defined. Now we will see some characteristic property of Raman lines. So these are some characteristic of Raman lines. So first is, the intensity of Stokes line is always greater than corresponding anti-Stokes lines, as we have seen already. Second, the Raman shift, means you can say delta V bar, lies within the far and near IR region. You can say in the IR region, or you can say middle IR region. Means that the Raman frequency are generally identical with IR vibrational frequency, but there is a change in excitation, and the Raman lines are symmetrically displaced above the parent line. Means what? When the temperature increases, their individual separations from the parent line decreases, and the frequency difference between the modified, or you can say the parent line, represents the frequency of the absorption band of the material. Now we will see. So it is clear, as we have seen in the lecture, we will see what is the major difference. So in Raman, what happened? Due to scattering of light by vibrating molecule, we are getting the spectra. Here in IR, result of absorption of light by vibrating molecule. So here there is a difference in a principle. Then Raman active vibration, change in a polarizability, and IR active vibration, change in a dipole moment. Here in Raman we can use water as a solvent, but in IR we can't use water as a solvent, as it will give a very highly intense peak of OH group. Here the method is a very accurate but not very sensitive. But in IR, method is very accurate as well as very sensitive. See, here our solvent is water, so we can use the optimal systems are made up of the glass, or you can say the quartz. But here, whatever sample holder is there, you can say, or you can say it is made up of the crystals such as CaF2, or you can say the sodium bromide. In Raman, the substances must be pure and colorless. It's a requirement. Here this condition is not applicable. Raman lines are weaker in intensity as we have seen, but it will be concentrated, or you can say you can increase the intensity of the lines by increasing the concentration of solutions. But in IR it is very opposite. The dilute solutions are preferred. You can't use the concentrated solutions in IR. So this is the basic difference between IR and Raman spectroscopy. Now in the next lecture, we will see the Raman spectroscopy in more detail. Thank you. If you have any doubt, you can email me on this email ID and you can contact me on this number. Thank you, dear learners. Wish you very happy learning.